So in that LSQ adjustment, we have discussed observation equation method, which is fxa is equal to la, the condition equation method, which is fla is equal to 0, and then mixed model in the last class, which was fxa la is equal to 0. So fxa is equal to la, the linearized version is v delta xa minus l. This was the linearized version. And bv plus w is the linearized version here. And bv plus a delta xa plus w is equal to 0 is the linearized version. So these are the models. And at the last, what we were computing is we are trying to minimize this VTPV by all means in all three domain, and that was our single objective. That is the basics of least square adjustment, that if your model is in any of the form above three form, whether it is in this form or this form or this form, we have to ultimately minimize this VTPV. But what is generally happening is that during your initial I'm just writing about the pre-adjustment and that post-adjustment scenario for uh, starting today's class. So we all know that how this X is estimated here. ATP inverse ATPL. You know how the data is adjusted here in condition equation method and here also in mixed model. So we are not discussing about the solution, and isn't it? Because there is a one book called Alfred Like, and there is a chapter 4 in that Alfred Wright book. The content for observation equation, condition equation, or mixed model very briefly is explained in this book that I'll share today also. Sumit, just remind me for sharing this book, because this book is very popular in understanding the least square adjustment. And after this mixed model, observation, condition, and mixed model, there is a term called sequential adjustment followed by Kalman filter. So that has been already discussed by Vipin. That is the advanced adjustment scenario. These are the research domain where the people are conducting the research. So these are advanced LSQ where you have huge data set that needs to be adjusted, as well as in this Kalman filter you want the prediction also, prediction about the future, so that you could correlate about your predicted values and the actual observed values. So these are the, I would say, these are the, some of the um, major highlight of adjustment. So these are the five popular methods. One is observation equation, which is very popular. Second is condition equation that needs your command over the problem. If you understand the problem very well and you have the understanding of writing equations for trigonometrical relationship and other equations, because every problem will have a figure representation. That figure will help you in finalizing the equations. And obviously if you do not have any other option, by separating the your model for or your mathematical equations in either of the form of observation equation or condition equation method, you have to go with the mixed model. But there are certain observation, let me just erase for the time being here. But there are certain ways where you will have certain bunch of data coming at you know coming at t is equal to t naught. Some of the data coming at t is equal to t naught, and then after t is equal to t1, you are having another flow of data set, and similarly t is equal to t2, you have another flow of data set. So when you have successive data set that is flowing into the system, then you preferably work with the sequential adjustment rather than working with the normal chain of events. Because let's say if you have working in a scenario where you have 24-hour data set, in each second interval, how to work with that, and that is the place where you work with the sequential adjustment. And then obviously the Kalman filter, which is an advanced domain, although the basic is the same, is that you use the least square adjustment. But Kalman filter predicts for, let's say you have data set for t is equal to t naught, t1, and t2. So Kalman filter predicts results or estimates for t is equal to t3. And then in future, you will go at t is equal to t3 and have the field data to see whether my field data actual have what is the difference between predicted by Kalman filter. So this Kalman filter is actually is the backbone of orbital estimation. So satellite is moving in the orbits. So before sending this satellite into the orbit, it's the trajectory of this orbit path, elliptical orbit part, is actually estimated by Kalman filter by set of normal previous observation, isn't it? So these are the some advanced topic that we were finishing today. What is our discussion point is, our discussion point is about the post adjustment and pre adjustment. So we all know that we have to minimize the VTPV because this is the benchmark for the least square estimation. Okay, so in this process of minimizing the VTPV, when we end the solution, we need to have certain criteria, isn't it? We need to have certain convergence criteria when our adjustment process will stop. So there are a lot of ways where one can think of uh, I mean think of the solutions for convergence criteria. Okay, and in the case of convergence criteria, many people have their own version of ending the iteration. Okay, so some previous uh, fellow have said that if your VTPV I plus 1 minus VTPV I, if their mod is less than, very less than the very small value called epsilon, that we have done in the soft computing of Newton-Raphson method and other iterative methods that we have discussed in BTech days. So that kind of threshold is actually needed to end the so-called the iteration. Some have also adopted like this, that delta x, which is nothing but the xa value at I plus 1 minus xa value at I, the mod of this should be less than epsilon, then we end the iteration. So when your least square adjustment process goes into this iterative system, you end the process at such steps where you have no change or almost no change between one iteration to another iteration. Okay. Second point is, this is the one thing which is about the end of the iteration. Another point is, what is more important is to make you aware about the choice of sigma naught square. So please remember, if you write sigma VCV, which is variance variance matrix, then you write like this, isn't it? Please remember, this is cofactor matrix, which is the scaled version. When you do not have any information about the actual variance covariance matrix, you work with a scaled version of variance covariance matrix, which is cofactor matrix. So when you write pre-adjustments, and so after adjustment, there would be things that would be written in a different fashion. We write post-adjustment in many books. You will write use as hat like this. So in this process of pre-adjustment and post-adjustment, you work in this two equations, where one which is without hat, which is pre-adjustment scenario, and another is post-adjustment scenario. Okay, so whole process of comparison or acceptance of your results lies with this fact that how you are comparing these two terms, which is we call it a priori reference variance factor and a posteriori reference variance factor. So these are the two major component that helps you in accepting the result, making a green flag over your adjustment process. How would you decide this green flag? Okay, so this green flag would be decided by comparing these two values, which is sigma naught square and sigma naught square hat. Please remember that sigma naught square is generally taken as 1 if you do not have any understanding about, or you do not have any experience about the data set, problem, or your understanding related to the situation. That means you are given a problem, you do not have any experience in that, you work with as 1, and then you try to see whether you achieved this as equal to 1, very very greater than 1, or very very less than 1. That you will see when we finalize the iteration or end the iteration. Okay, so that is one major issue, and that sigma naught head square will be computed based on how your cofactor matrix after propagation, isn't it? How your cofactor matrix is computed. So this is one good point to add to make you aware that when you finish the iteration, you all have the variance covariance matrix for all possible. Let's say if you talk about the observation equation method, you have a variance covariance matrix for XA, you will have variance covariance for VV, variance covariance for LA. So you have all these variance covariance matrix post adjustment. And when you have this matrix post adjustment, or if you simply have QXA, QVV, or QLA, then using this you will find out what would be the sigma naught square hat for converting from one to the second one. So this will be based on your numerical solution that you are achieving while performing the iteration. So again, just to make you familiar about least square in a summary, in your LSQ adjustment, it gives blue solution. Blue solution means best linear unbiased estimator. What is estimator? Estimator is something which help you estimate something. In our case, we are estimating the x through least square solution. So it is a linear estimator, unique value, unbiased, consistent solution, choice of weight matrix, minimum variance, maximum likelihood. So all are the properties of the so-called least square estimator. And for normally distributed data, LS approach is also the maximum likelihood approach. Please remember, when we started this least square adjustment process, we derived this what is the least square by using the concept of maximum likelihood. Okay, so what are the assumptions? Assumptions were again in the least square are very simple, that expectation of the error was 0. What is expected from any error or any residual? That it should be 0, but their variance would be given. The variance of the particular error would be given. How much error is varying with a particular observable. Although we do not want any kind of residual, but what is expected from the residual? It should be 0. The mean of error should be 0, but it is supposed to have certain variation, or it is expected that all residual should have same variance. So these were the assumptions that we have taken into account. Apart from this, we've discussed that the characteristics as independence observable, normally observable, you know, the that data should be normally distributed and observable should be independent. Okay, so these were the criteria that we followed for solving the for initiating the, I mean, these were the assumptions before initiating the least square solution. The assumptions, these assumptions that we discussed in the slide form way before, that were before the starting the adjustment. While starting the adjustment, what were our observations? Oh, sorry, assumption were the linearity should be imposed in the sense that the model in which observables are expressed as a linear combination of the parameter. There's a fxa is equal to la is a function, so it is expected that you devise in a way to which your model should be linearly representable. Okay, so that we have done. Then after this, we also told you that ATPA inverse ATPL is the solution for X. We derive this, isn't it? But in this case, it is expected that the rank of your A should be equal to rank of the the number of the parameter, and this matrix should not be ill conditions. We have to choose the values of sigma naught square such that, because ultimately you would be using P is coming from, if you are properly, if you properly remember this P, which is, we call it as a weight matrix. Weight matrix is never given in any problem. It is never expected that you are given with weight matrix, but in general we know that it is inversely proportional to the variance square. So we already have sigma LB in a problem, so we work with sigma naught LB inverse for computing the weight. But in that case, we have to understand that doesn't this equality doesn't hold until you open this sigma naught square. You work with sigma naught square. So this sigma naught square term, which is coming automatically here to hold this proportionality sign, which is nothing but as a constant, it should be chosen in such a manner that it works as a reference variance, as well as it helps you that your this matrix, which is automatically coming after multiplication of design matrix with weight matrix, should not be ill conditioned. Okay, you should have the inverse, then only you will probably get the solution. If you do not have the inverse, then it is not possible to get the solution. Okay. So not all iterative processes necessarily converge. Some may diverge, other may oscillate or repeat themselves in certain cycle. Yet others may converge, but not to the desired solution. That is also a possibility. These are the numerical aspect of least square solution. That means you never have such scenario when you will only converge. Okay. Sometimes you get a sinusoidal solution, so that is also expected. That goes with time, it is changing. And which is the example is one good example is the geometric sorry, during the pre-processing of the remote sensing data, and when you try to perform the resampling operation before radiometric correction, at that moment you have this kind of, if you choose too many GCPs for converting the image to map coordinates, then if you choose too many GCPs, then in that time the model which has to be best fit as a image, best fit the image so that you could convert from image pixel to map coordinate pixel, but it doesn't behave in same fashion, it behaves sinusoidally. So that is another example where we try to focus that our least square solution have different properties in terms of solution also. Anyways, these are just the basic summary for you to understand that it is not always that your solution would converge. Some situation will arrive where your solution may diverge, oscillate, repeat themselves in a certain cycle. Still, yet others may converge, but not to the desired solution. So that is another way of representing it. And obviously, I told you about the iteration. There is no problem in that. You can choose any iterative solution or convergence criteria that I have told you between I plus 1 and ith iteration. You can choose any relation. I've told you some of the popular one, but it is accepted that some other criteria could also be. There is a possibility that there should be other criteria also, but it has to be properly justified. Okay. So these are the iteration and convergence criteria. Now we come to find out about the solution strategies. I mean, what are the issues of uh, so-called priori variance sigma naught square in the observation equation case. So let us focus more on the sigma naught square, because this is very important. Many a times these are asked in the interview of PhD interview, and many I mean companies interview where you go for analytical companies. people ask you about these a priori reference variance, which is very popular. So arbitrary, we choose as this value as 1, isn't it? We do not worry about how these value would be given, but we arbitrary, we choose this value as 1. So these estimated values, it does not, it should not influence in general, but arbitrary choice of a priori variance factor sigma naught square does not influence the estimated values of adjusted parameters, adjusted observations, adjusted residual, and estimated variance covariance matrices of these adjusted values. This property of variance factor can be easily chosen. That means whatever you are estimating, this sigma naught square value does not influence the estimation. That please remember always. You may be thinking that okay, sigma naught value square is given, but it does not affect the estimated values of adjusted parameters, be it LA, sorry, not be it X, or be it L adjusted matrix, residual matrix, and associated VCV. Okay, so that you can easily prove, there is no issue in that. What is more important is what will happen if we, if you try to see uh, what will happen if you choose or provide a value of a uh, value different than sigma naught square. So how where do you change this value? So obviously if you change the sigma naught square to let's say any value, maybe 1.05, let's say change to 1.05. So what will ultimately change in this our observation equation method? We are using ATPA inverse, isn't it? ATPA inverse ATPL. So here in A, we do not have any influence of sigma naught square. Why? Because A is a design matrix. Design matrix comes from this del fxa upon del xa at xa is equal to x naught. In this whole equation or derivative or Jacobian, we do not have any influence of sigma naught square. Sigma naught square is written where? When you write sigma is equal to sigma naught square q. Here it is written. Okay. So you do not have any influence on A, you do not have any influence on L, you only have this influence on P. Why? Because P you generally estimate from variance square, and you, in order to remove that proportionality sign, you use the sigma naught square. So if you change the value of reference variance to 1 to 1.05, the change, associated change will only happen in this P. Okay, the weight will change. So these if you try to work like that, this ATPA inverse ATPL, and if you change this P to alpha P, or let's say convert this value, so AT alpha P A inverse AT alpha PL. Okay, and then you again rearrange, you see that AT PA inverse alpha inverse alpha ATPL. So again, this alpha and alpha inverse is identity, because you cannot have only replacement only one position. You have to replace in this T to multiple both positions, and that will take you or that will help you to make it out that again ATPA inverse and ATPL is will be there. So weight change in weight doesn't happen, and it does not uh, change your x. So that is proven, that is easily proven. Okay, so in fact you can similarly see that's so called the variance covariance matrix. So let's say sigma xx axa hat will be given by sigma naught hat square n inverse. Now please remember, we have estimated qxa we have estimated as n inverse, and sigma xa hat would be given by sigma naught square hat QXA. So it would be given by sigma naught hat square and multiplied by n inverse. What is sigma naught hat square? We all know that it is VT PV upon n minus U, isn't it? And then multiplied by ATPA inverse. So when you replace again P by delta P, alpha P, sorry. So here this alpha, again this alpha inverse. So it will again same. So what is my point is? My point is, although you have taken this sigma naught square as 1, it doesn't alter the solution if you replace this as a 2 or 4 or 5 or 10 or whatever it is. This is what we have proven. So the question is, if it does not affect, because I'm my discussion started with this point that today we have to focus more on the sigma naught square part. So if it does not affect the parameters that are estimated or the variance covariance matrices that are estimated, so where it does it affect? Because if we change the sigma 1 to 5, 5 to 2, or whatever it is value, so where it does affect? Okay, so it is said that elements which are affected is that some of the intermediate results are affected by assumed sigma naught square. I mean, not the final, but the intermediate. I mean, I'm talking about the middle steps that we have seen during the derivation. One of the middle step was the normal equation matrix. So we have simply estimated the n. N is as ATPA inverse. I'm hoping that you are practicing these derivation quite frequently, so that you would be also writing I mean these equation very frequently, because they are very easy. They are not difficult. You do not have to write complex equations. You just have to write the matrices multiplication, then their inverse. Okay. So the normal equation vector of absolute terms u and the estimated variance factor sigma naught square. So it is expected that it is it is it is expected that we have certain intermediate results that would be affected. Okay. If we simply say that what is the value change in value of n, so yes, it will be changed, because there is, you have to choose alpha p, it will change. You simply use a ATPL. If you choose alpha, it will change. So these are the intermediates. They will change. Okay. So these are the one critical 2 3 points. Then the condition of the so-called n, which is ATPA inverse, that will also reflected with a different value of sigma naught square. So to help making the normal equations coefficient matrix n best conditioned for inversion, because we have to take the inverse of this matrix. So what we can do, we make this matrix good condition, not ill condition. Otherwise, if we make this our matrix ill condition, inverse would not be possible. And if it inverse is not possible, then we may not get the solution. So that is the chain of events. So what we can do, we have to improve the condition of a matrix called n. How? This, we have to choose the appropriate value of reference factor. That's why in order to avoid any such cases, we generally choose this matrix as 1, n, sorry, n sigma naught square as 1. But in some certain cases, it is not possible that only choosing this value 1 would solve your purpose. Okay. So this happens when the magnitude of element of this matrix are close to 1. Okay. And n is equal to, we know that it is ATPA. So we can choose the value of a priori variance factor to produce the reasonable relative weight matrix P, which makes the n matrix well conditioned. Please remember, P is the one which is very critical here. That's why we give more discussion towards the weight, how you are choosing weight. If you do not have any idea, that's why when we say we choose identity matrix, if three observations are in the picture. Okay. So if weights are to be chosen by observation variances that are given in the problem, you have to be very careful about how you are choosing sigma naught square. Sorry, uh, how you are choosing sigma naught square in your problem. Okay, so that is one thing.
सर सर
Hello,
हाँ सर मैं आज समथिंग
कौन बोल रहा है?
सर सुमित सर
हाँ बोलो.
सर आपने बताया कि अल्फा जो है सर वो ए को इफेक्ट नहीं करेगा बट पी को करेगा सर जब हम यहाँ पे बीच में मल्टीप्लाई कर रहे हैं सर वी टी अल्फा पी भी करें तो कोई इफेक्ट नहीं आ रहा है सर सपोज हम वी टी पी अल्फा वी करें तो क्या उसका इफेक्ट आएगा सर
किस पे?
सर जब हम अल्फा को इंट्रोड्यूस कर रहे हैं सर सपोज वी टी पी वी के बीच में आपने अभी इंट्रोड्यूस किया था तो सर
हम्म.
वहाँ पे कोई इफेक्ट नहीं आ रहा था डायरेक्टली इक्वेशन जो एज इट इज आ जा रही थी तो सर अगर हम उसे पी और वी के बीच में अगर मल्टीप्लिकेशन में इंट्रोड्यूस करते हैं तो क्या इफेक्ट आता है क्या इसकी पोजीशन चेंज करने पे इफेक्ट आएगा सर
I'm sorry, but this is a very stupid question. The reason is simple. I'm not telling you that I'm not introducing alpha beta. Please remember, I'm not introducing alpha. First, you should mute yourself. Your voice has a lot of background noise. Please remember, I am not introducing only alpha. Please remember, this is your original P matrix, let's say. When I write alpha, that means I am multiplying these component by something. Alpha is a coefficient. It is not a matrix which you are thinking that if you multiplied here, if you write p alpha also, that is multiplication by a factor called 2, or a value called 2 could be anything, 0.05, 1 by 10, whatever it is. These, I'm just trying to explain, if you change your p matrix by scaling up or scaling down, it doesn't affect the final deliverables. That's what I'm trying to say. So that's why I called it a very stupid question, because alpha placement I'm not talking about. I'm talking about a new p dash, which is alpha p multiplied with a new value to this original p. You get my point?
yes sir now I got it I thought sir alpha something else sir thank you sir
No, alpha is not a matrix. Alpha is a coefficient that is scaling the weight matrix. Why? Because I told you na here, this weight, let me just highlight so that you see where I'm writing. This weight is inversely proportional to this variance of the observations. Okay. And then in order to remove this proportionality sign, you introduce a coefficient. This coefficient generally is considered as 1, but let's say if you have chosen as 2 or 0.05 or something else, so it doesn't affect your final solution. That's what I'm telling you by explaining this through placement of or deriving it by certain placements. Okay, so role of sigma naught square is very important, because this will change the whole picture. So it will improve the condition of the matrix. Second is hypothesis testing. I'll discuss more about the hypothesis testing in today's lecture, but let me just clarify certain thing. So hypothesis testing is just part of statistical testing. Statistical testing means, I don't know how to explain statistical testing at this point, because I have not informed you about a little more basics yet. But to be very frank, hypothesis testing is a part of or part of statistical testing, which helps us, or which gives a green signal to our adjustment results. I mean, after the whole rigorous adjustment procedure, who will tell you that your results are now good to go? So that has been given or uh, provided with the help of statistical testing, and this whole process is named as hypothesis testing. You please understand this part very much, that we do not end the adjustment process just by finding the value of x. Please remember, we have to find out or provide the statistical basis or statistical support to our answers, and that is this statistical testing part for of the correctness of the least square adjustment is known as hypothesis testing. And there are 3 point of view. One is to observe the quantity should be free from systematic errors. The relative weight of the observations should be reasonable and as expected in practice. Please remember, again, these two quantities came. Your whole adjustment process, which, and please remember, this least square adjustment which we are discussing now, it is for those observations which contains only random errors, because otherwise our whole discussion steps would be different. We are not considering the systematic errors. We already removed systematic errors. We already removed the so-called gross errors or mistakes or blunders. The only errors that remains is random errors, because that's what our initial discussion that started in this class, that we have to remove those random errors that follows certain probabilistic nature, that is not deterministic in nature. And second point is the relative weights or assigned variances of the observation should be reasonable and as expected in the practice. And the third one is mathematical model should be realistic, representing the true relationship between parameters and observables. Okay, so hypothesis testing will only be applied if these guidelines would have been followed. Okay, um, uh, otherwise the statistical support that we are talking about is of no use. And please remember, it's very easy. The statistical testing part is very easy, because you just have to work with tables, uh, and just have to formulate the equations. Because in the statistical testing part, you do not have to derive anything. You just have to use the tables, and you work with tables, and you find the critical values, and your result should be within that critical value. Okay, so what we do in our least square assessment, we generally test these two values, or compare between these two values, the sigma naught hat square and sigma square. Okay, that means the estimated variance factor and the assumed variance factor. So this is your estimated. How? This is estimated by. What is this? This is assumed. Sometimes normally as 1. You understand this part? After last iteration, this is the ith iteration. That means ith iteration, you could say, or last iteration. That is much better word. After last iteration, you will get the value of v, final value of v. So when you, how do you find this VTPV? You find this VTPV hat by finding the last iteration value of residual. N minus you divide by n minus. As you assume this sigma naught square as 1. So to test the above, you find the ratio of the estimate which was found to follow some probability distribution must be statistically tested. Is everything is consistent? This relationship has to be 1. This, that means this division, sigma naught hat square divided by sigma naught square, has to be 1. Otherwise, if it is not 1, times you, it is a very good chance that it should not be 1, or maybe not be 1 always. Then what is expected, that this relationship must follow within the desired limit. This limit, हम लोग एक दूसरे से कहते हैं ना भाई, लिमिट में रहिए, ज्यादा नहीं उड़िए. तो अगर आप आइडियल नहीं है, आप आपके अंदर वो कैरेक्टरिस्टिक नहीं है जो आइडियल स्टूडेंट्स में होती हैं, तो आपसे कहा जाता है भाई लिमिट में रहिए, ज्यादा नहीं. तो वो लिमिट है ये. This limit has to be given only by certain confidence that are given posed on the solution. Anyways, so just for understanding purpose, if it is not 1, then the limit you have to estimate, which this limit is also called as confidence interval. Okay. And what if this ratio is very large than 1? What if this ratio is very less than 1? So ratio is too small than unity. That means that indicate that when it is too small, please remember, that means too small than unity, इसका मतलब आपने सिग्मा नॉट स्क्वायर को ज्यादा चूज किया है सिग्मा नॉट हेट स्क्वायर से. ओके इसका मतलब है इंडिकेट दैट वी आर वेरी पेसिमिस्टिक. पेसिमिस्टिक मींस आप समझ रहे होंगे, ऑप्टिमिस्टिक का अपोजिट होता है पेसिमिस्टिक. इन वेटिंग द ऑब्जर्वेशन, alternatively the used observation are more precise than we are expecting. When ratio is more than unity, इस केस में क्या होगा, indicates that we are very optimistic. That means we have यही साइन होगा ना, indicates that we are very optimistic in weighting the observations. Alternatively, the observations are less precise than we are expecting. Thus, the assigned variations should be increased or the relative weight should be decreased. We also say that this could be because of any systematic or gross error causing very large values of residuals. That's why very large values of residual means if these values are very large, if these values are very large, then only this sigma naught hat square would come as very high, isn't it? So review the model. If all the residuals after examination were found reasonable, we start to blame the assigned weights of the observation. We can then decrease the weight by this ratio, or equivalently variances should be increased by this ratio. So we carefully examine the model again from the very beginning, if this is the scenario, to make it a realistic distortion of the our observations. Okay, so this is in a nutshell is your comparative steps. But why this understanding of hypothesis is important is because it came as the last step of your adjustment results and very important in understanding the whole picture. Okay, so what I'll do today, I'll share the overall methodology also. Please, Sumit, you have to remind me so that everybody should have this access to overall methodology, complete methodology, because now it is a two and a half page summary steps. I will share these steps, these 2.5 page steps on how to follow when you are solving through observation equation method. Because everything is explained, there is no need to explain re-explain everything. You have all understanding, you know how to write those equations. But what I'll do, I'll share these these steps to you so that one by one you should know what to do when, if a problem is to be solved by observation equation method. So I'll share this methodology. You will go through it, and probably on Tuesday or on next Thursday we will discuss it if you have any queries. Okay. Okay, so this ends here. Now our next topic of discussion is just a moment. So we will discuss about few more distributions and confidence interval initially. First, we'll discuss about few more distributions and then confidence interval, followed by, we'll go with the hypothesis testing. Very simple, no need to worry about it. So in the case of statistical, a few more statistical distribution means we already know about the normal distribution. There are other distribution which are very popular and thoroughly used, that we have to see. So let me just start it with one figure. Okay, so in this a part of understanding the so-called confidence interval, or different uh, sampling uh, distributions, let us first focus on so-called distributions which are generally being given to tell something about the population. So generally what happened, you have population and then you have sample. So sometimes what happens, you have so much huge data set about the population. Let's say our country's population, isn't it? Let's say our country's population. So we do not know the exact mean weight of a particular age. Let's say if somebody wants that in our country, what is the average height, weight, and so on of a person, no, without gender specific, what is the height and weight of a 25-year person? We do not know it because that is a huge population. Many people will be of 25-year age. Or let's say if we make a range of this one, we do not know it. What is it? We just only have certain idea. We do not have any conclusive idea also, but we just have simple idea. So in that cases, when we do not have any information, and there would be a lot of cases where you have population that consists of so many huge data set that you cannot comment anything, then you do not have any choice but to work with sample, isn't it? I hope you are getting it. If you have any confusion in this, you can ask right now, because what is our discussion point starts with only this assumption that we are, or we have certain cases where we do not know about population, we do not have anything about the population. Okay? And then at that time we should work with samples, but sample has to be representative of the population. Representative in the sense, if we are talking about 25 to 30 year of age group, we should not only select the samples from Uttar Pradesh only or Madhya Pradesh only. We have to make the sample representative, and it should be from all states. Why? Because some states may have different height, uh, uh, I mean, of a particular person or a weight of person. So, in order to have a representative scenario, the sample has to be representative. Okay, that is one thing. Second thing is that size of the sample becomes very large, the mean and variances of the sample should be close to those of the population. That means if we have very large samples, then the mean and variances of those sample should approach to the population. So let's say if you're talking about population, that will be represented by mu and sigma square. We do not know about mu and sigma square. We do not have any idea. What we have is the sample mean and sample variances. These are of the sample. We do not have any idea, but we have to work with this and find out the, can we find out Answer is no. We cannot find out. There would be no relationship. But what we can do, we can make a range of interval. That would be a function of. So we can have any idea about mean and variances with the help of sample mean and sample variances. But only this function will not help. Again, that is also a critical case. Only this function will not help. What will help us more if we know about the associated distribution? Okay, step by step. So we can only comment about the population mean and variances if we have idea about the how the sample distribution is there. Okay, associated distribution. So in the case of a random sample set for a population, let's say four set are given: set 1, set 4, 2, set 3, and set 4. I'm just taking, there are 10 values in set 1, similarly 10 in set 2. These sets are prepared just like I've assigned four of you to take four set samples from the population. So Sumit, Alok, Shivam, and Rahul and went down and collect four samples. The four sample have these values. So let's say four students have taken the samples and they will have four values. Okay. Now, which one of the sample is true representative of the population? Who will tell us? बताइए आप लोग guess करिए. Which one set is, you could consider this as a true representative of the population? Can you comment on it?
No, sir.
Why? बताइए, जिन्होंने नो बोला वो बताएं भी तो, आगे भी तो बताएं.
Sir, since there is no relationship between sets and means any result which we can derive, sir.
नॉट जस्टिफाइड. फिर से बताइए. सुमित आप बताइए.
Sir, I was only telling, sir. So since we have set values, then we got the observations, and uh, then, sir, we should have some kind of relationship so that we can reach up to some range of solution.
Sir, we have not any mean value.
हम्म.
Sir, mean value कोई नहीं है sir इसके.
चलिए, एनीवेज, चलिए मैं जो बताना चाह रहा हूँ वो ये है कि सपोज यू हैव 10 सेट्स ऑफ सैंपल्स. सो जनरली people will incline towards sample with that is having less variance. Okay, so it is normal trend that public chooses that particular observables, that particular sample that has the less sample variance. but it is a mistake that we should not commit. The sample variance should not be a deciding factor about whether the sample is a representative of the population or not. Because let's say in this case where I have taken the example, the population means is supposed to have this value of 26.1. So 27.9 is very farther from 26.9. The best representative would be 26.9 cases, but their variances are very high. So that's this example helps us in suggesting that we should not get biased towards sample variances in deciding about the representativeness of a particular sample. Okay. So if a sample fifth comes into the picture and it consists of 50 values, let's say, and again it has 27.0 and variance as 10. Still, although we know that population mean is 26.1, so we should not give more weightage to the sample which is having nearer mean value or a variance. We should give more weightage to sample that consists of a large data set, that is 50 values. Although its sample size, despite the increasing the sample size, it is not nearer to the population mean, but we should give more weightage, although considering that all the samples are representative, they are unbiasedly collected from population. So this is the sampling distribution theory. Okay. And in the sampling distribution theory, you have three types of test, which is very popular. One is chi-square test or chi-square distribution. In the chi-square distribution, which is symbolized as this, compares the relationship between population variance and variance of a sample set based on the number of redundancies in the. So this is the chi-square index. Chi-square index is S represents the sample variance, sigma represents the population variance. Okay. So if random sample of n observation y1, y2, y3 up to yn is selected from a population that has a normal distribution with mean mu and sigma square, then by definition the sampling distribution, chi-square sampling distribution would be given by this, where this is degree of freedom, which is n minus 1, n is number of observation. Again, assumption is very common that chi-square distribution we are planning here is for a sample which has been drawn from a population that has normal distribution and a mean value of mu and sigma square. So you are having a sample that has been drawn from a population, and population is having NDC, normal distribution. Okay. How this curve would look like is a little asymmetric, and this is a critical value where we do not want any observation in this particular region. Please remember this representation is of this. This is we are representing here as, it is not x. Please remember it is chi square. Na? So it is v, chi square alpha v. What is alpha? Alpha is a probability with which we are defining the critical value. Now, what do you mean by critical value? What is expected that this relationship will have a value, isn't it? For a different s square and a different sigma square, and for different degree of freedom, this will have a value. A value. It is expected that this value should not fall here. is very common. You can easily pick it up and understand that you know this is very common to see that any such value should fall here. This is a region for this ratio. Which ratio? It is expected that it will fall here. What is not expected? That it should not fall here. How this region will be decided? Because this bar can continuously go here and here also. So this will be decided based on the selection of this alpha. What is alpha? Alpha is known as your so-called probability levels, or we could also call it as a certain percent probability with which you are calculating this chi-square value. Okay. For example, let's say if I'm telling you one problem that let's say what we have to find out the 1%. Please focus on my question, that we have to find out the 1% of the area under the curve having 10 degrees of freedom. Okay. So 1% of the area, that means 1% representing 0.01, that becomes the alpha. 10 having 10 degree of freedom, this is degree of freedom. This is DOF, degree of freedom. So if this is the case, 1% area under the curve, that means alpha is 0.01, and degree of freedom is 10, then we'll go with the table. A chi-square table would be given in your book at the last. Then you'll go with the alpha value and degree of freedom value. So column would be alpha. These alpha values are written here, different alpha values. And in the rows, the degree of freedom is written DOF and alpha ऐसे करके लिखा होगा. आपने इस वैल्यू पे जाके इंटरसेक्ट करना है, 10 की वैल्यू और 0.01 की वैल्यू, ये इंटरसेक्ट आप करें. This intersection means 23.21. This value would be given. Then this means that 1% area under this curve lies in the upper tail. This is called as upper tail. This is called as lower tail. In the upper tail, between this value, this critical value, which is 23.21 to positive infinity. Very simple. The question can be reversed again. Somebody could ask, what is the 1% area under the lower tail or near the lower tail? That means you do not have to find out the area under the curve in the upper tail region. That means in this region, you do not have to find the area under the curve in this region, but instead in this region you have to find out this lower tail region. Again, question remains same. Here we worked with 1% as 0.01, but the whole area under this curve is 1. 1 minus 0.01, or your so-called 1% would become how much? 0.99. So the similar table, you have to go ahead with 0.99. When you go and find a value, that would come as 2.56. That means area under the curve in the lower tail, 1% of the curve would come be 0 to 2 point. That means 0 to 2.56. let's say this is 2.56. So this would be the area under the curve 1% near the lower tail. You understand this problem? It's very basic. Just you have to work with the statements. What statements you are making. Again, I'm repeating because this is the new. But please believe me, this is the only topic that goes into your mind in a different manner. Student to students, the understanding is different. Sometimes your statement would be right, but I am not able to understand it. When you explain it through figure, it would be okay. So what the reason is very simple, because the conceptual understanding in the case of hypothesis testing, confidence interval is little tricky. Sometimes people devise their own mechanism to understand the problem, and that's true. That's very true. There is no issue in that. But the only issue is that will only happen if you read from your own. Do not expect that this small video lecture will help you out, because I am only explaining the very basic quantities or statements that help you out when you read the content from the book. But please remember, these statements that I am making, that what is 1% area under the curve from upper tail, what is 1% area under the curve in the lower tail, and that's how we are differentiating between the values. It's very easy. It's very simple. But you have to read it again, find the values from your own on from the table, then write this value from your own, and then make sure that you are confident enough to find the values, find the answers. Okay. So this is one sampling distribution. I'll discuss some numericals also, but before that we'll see two other important distribution, which is called as student distribution or T distribution. Other name is T distribution. T distribution is for used to compare for population mean. So please remember, chi-square distribution is for population variance versus sample variance. But here we are comparing the population mean with the sample mean with the given number of redundancies in the sample set. It is very similar to normal distribution, but for small number of observations. That means normal distribution applies to the whole population, but the T distribution is only applies at the sample data set. Okay, this distribution is preferred when your observation is less than 30. If your observation is greater than 30, you will go back to the normal distribution statistics. Please remember always, this T distribution is for n is less than 30. What is this? If Z is a standard normal distribution or a normal random variable of a defined data set, okay, the chi-square distribution is a random variable with the mu degree of freedom. Then T distribution is given as Z upon this. That means Z is T is equal to Z by square root chi-square by p. This is your T distribution. Okay. So T values for selected upper tail percentage versus the T distribution with the various degree of freedom are given in the table. So there is no need to worry about it. You again have to work with the table. And for a specified degree of freedom and percentage points like alpha, which we have discussed in the previous example, will help you out in finding out the correspondence, corresponding the T values that we find out from the table that correspond to the area alpha under the curve between the tabulated values T to infinity. Okay. So it is a symmetric curve. So whatever happens in the upper tail would be exactly reflected in the lower tail because it is a symmetric in nature. But the previous chi-square distribution is asymmetric. Please remember these two figures. This is asymmetric figure. I intentionally drawn this figure like this because this is asymmetric. This is symmetric. So whatever happens in the upper tail, that will remain in the that will also be same in the lower tail. Okay. So so with this normal distribution, the ranges, percentage points in the ranges are given in the uh, point 0.4. Okay, so let's say for example I'm asking find the t value relating to alpha 0.01 with a 10 degree of freedom. So you go and you find in the table. The table will again you have to look like this: alpha here, degree of freedom here, degree ये degree of freedom है mu. So you will again go into the table. You will find out with the help of alpha and degree of freedom. You will see that at this intersection the t value is for particular 0.01 alpha and mu as 10. You will find a value which is written as 2.764. So that means 1% of the area exists under the t distribution curve having 10 degrees of freedom lies between due to symmetry is 2.764 to infinity. This critical value these are the critical value I'm highlighting. It is t alpha, yeah, t alpha. Okay, this is the 1%. Similarly, symmetry of the curve, the same value of t alpha will be minus infinity to minus 2.764. So positive to infinity, 1% on the right side, negative to infinity. That is t statistics. Now, these are the two distribution, popular distribution. Very easy. We can find out the confidence interval for mean. The confidence interval for mean is given by t distribution. Again, I'm writing z upon pi square a. Z you already know, x minus mu by sigma y. अभी मैं इसको ओपन नहीं कर रहा हूँ. I'll just wait so that you understand this part. Z क्या होता था? X minus mu by sigma. ठीक है, इसको मैं फिर से लिख रहा हूँ ताकि कंफ्यूजन ना हो. एंड स्टैंडर्ड नॉर्मल वेरिएबल आपको बनाना है किसका? सैंपल डेटा सेट का, सैंपल स्टेटिस्टिक का. तो सैंपल स्टेटिस्टिक्स क्या है? y बार मीन है और सिग्मा वुड अपीयर हियर एज ए सिग्मा बाई रूट एन. वाई? क्योंकि ये y बार का सिग्मा है. y बार का सिग्मा मतलब क्या हुआ? y बार का सिग्मा मतलब हुआ आपका जो मीन का वेरिएंस होता है वो सिग्मा बाई रूट एन होता है. सो y बार माइनस म्यू अपॉन सिग्मा बाई रूट एन डिवाइड बाई, आप इसको ओपन करिए, ये क्या लिखा होता है? एस स्क्वायर अपॉन सिग्मा स्क्वायर डिवाइड बाई म्यू. ओके, एस बाई सिग्मा. ओके, when you open it, it will go as a by root. So this would be the final open after opening the. So what we are expecting for population mean, आप फिगर बनाइए. हर चीज फिगर से बहुत आसानी से एक्सप्लेन हो जाएगी. हमेशा फिगर आप जरूर बनाइए, तो फिगर से आपको काफी चीजें आइडिया मिलता है, चाहे मैथमेटिकल मॉडल बनाना हो या कोई भी प्रॉब्लम हो. Now, whenever you are asking for population mean based on sample mean, your objective of finding out the range within which the population mean would follow, what you do, you expect it has to be in the major region in the sense you want that your population mean should come between this, because that is where you can claim that my sample was the best representative of the population. क्या आप ये एक्सपेक्ट करते हैं? क्या आप ये एक्सपेक्ट करते हैं कि आप जो सैंपल लें, the sample that you have drawn from the population should tell you about the population and that value of population would fall here? Answer is no. It's very easy to understand that you do not want your uh, uh, estimates or deliverables to be fall in the tails. You should give more weightage towards the central portion. In fact, you have to ignore these tails. And when you do so, what what is expectation? What is your expectation? That how do you write? You will write probability that थोड़ा सा जेई मेंस की जब तैयारी आप लोग करते रहे होंगे, आई डोंट नो वेदर यू इन योर टाइम जेई मेंस वर देयर और नॉट, but in your mathematics days while preparing for engineering entrance, you have solved too many problems for this. Mod z less than t would fall would I mean forces the z to be fall between minus t to t. That's what is written here. But with which, how much probability? 1 minus alpha, because alpha is this. So 1 minus alpha is, what is your z? Z is your again, you open that probability zone, open your probability zone. That means minus t to t. I'm opening this mod and writing this model. I'm explaining for alpha by 2. See, if somebody has given that, tell me with 0.05 probability level or 5% probability, or with the or maybe better statement would be if somebody says that, tell me with this set what is the 95% probability that range of the me. That means you will be given with the degree of freedom. Degree of freedom would be given. The associated data sample characteristic would be given. So you would be given all these value, let's say, in the problem. And I am asking you, tell me with 95% probability, what would be the range of the population mean? So with 95% probability, you are asking me about the confidence interval of the population mean. That means this is the 95%. So where are the 5%? The high percent here and high percent here. That means 5 by 2 here, 5 by 2 here. So this means this critical value is T alpha by 2 comma mu, T alpha by 2 comma mu. Here positive, here negative. That is the, now with values are given, you can find out, you can put in Y, you can put in S, you can put in N, and from the table, you will see, you will go alpha by 2, you will go degree of freedom, you will put in the values. That will give you the mu. Okay. Similarly, if I'm asking you the confidence interval for the population variance, तुरंत फिगर ड्रॉ करिए. This is your chi-square distribution table. Sorry, chi-square distribution figure. Again, what you want? You want your population variance to be fold here. Why? Because this is your distribution that is expected from your distribution. Right? Probability chi-square should be greater than chi-square alpha is equal to alpha. That means आपका chi-square जो है वो इससे ज्यादा आना चाहिए. ये क्रिटिकल वैल्यूज है, ये सारी क्रिटिकल वैल्यूज है. तो आपका जो ये chi-square है ये इससे ज्यादा आएगा तो आप इस रीजन में आ जाएंगे. किस रीजन में? वही अल्फा परसेंट 1% वाले में. Please remember in the previous example, let me just go back to that previous example that will help you better. देखिए वैल्यूज 2.56 से बढ़ के कहां तक जा रही हैं? 23.21 की. आप खुद ही देखिए, यहाँ पे 2.56 थी, यहाँ 0 थी, बढ़ी 2.56 और बढ़ी 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 और ये वैल्यू 23.21 पहुंच गई. इसके आगे 23.21 से ज्यादा होगी, ग्रेटर देन दिस रीजन. दैट मीन दिस रेड पोर्शन वुड हैव greater than 23.21 where you do not want. So if you write your probability level like this, answer would be wrong. आप इसको ऐसे नहीं बता पाएंगे. How do you write it? Again, chi square 1 minus alpha by 2 comma mu your is equal to 1 minus alpha. तो अब हम कहां पहुंच गए? अल्फा रीजन था, आपने अल्फा के लिए क्वेश्चन किया, हमने अल्फा को अल्फा बाई 2 इधर, अल्फा बाई 2 इधर डिवाइड कर दिया टू मेक यूज ऑफ बोथ एंड. हम इधर भी नहीं चाहते अपना आंसर, हम इधर भी नहीं चाहते, हम बीच में चाहते हैं. वी वांट दैट डिस्ट्रीब्यूशन इन द मिडल. सो हमने क्या लिखा? प्रोबेबिलिटी वी डू नॉट वांट हियर, वी डू नॉट वांट हियर, वी वांट अवर आंसर फ्रॉम बिटवीन दिस टू. तो अगर हम आपसे 95% बोल रहे हैं तो जो 5% आपको पता चल रहा है वो 2.5% इधर और 2.5% इधर. 2.5%, 2.5%. कैसे लिखेंगे? ओपन करिए. chi square 1 minus alpha by 2 mu. This chi square is written as आपको पता क्या करना है? सिग्मा स्क्वायर. बिकॉज दिस इज यू डू नॉट नो. पलट दीजिए. द मोमेंट यू रिवर्स इट, the equality sign will reverse. You understand this part? तो जो पहले इधर था वो इधर आ जाएगा. ये आपका पॉपुलेशन मीन का इंटरवल हो गया. There is very interesting point which I am trying to highlight here is that if you are following the Mikhail and Gracie book, please see in the table first कि वो अल्फा कहाँ से बना रहे हैं. If they are increasing the alpha from here, table has to be prepared according to that. And in some books, table is given alpha increasing from here. So you have to see the figure first in the table. Just above the table, they usually uh, present the figure of the distribution and the scenario of alpha. Okay, so that would be, would be much more easier to inform you about the figure of the particular distribution. Sumit, is it visible?
Yes, sir, it is visible, sir.
Okay, okay. So with this conference interval, I'll share the certain pages from where you can solve for the equation. Now next is hypothesis testing. Hypothesis testing is nothing different. It is only use of these tests. I mean, I would say the use of the chi-square and t-test, okay, to give you the flags, the green flags that we are requiring. Okay. And this hypothesis testing has certain steps that I'm trying to give you here. That hypothesis testing, during hypothesis testing, it is expected that you should tell us about the whether the interval, that means this the interval which we are designing for population mean as well as sample sorry population variances, they actually contained the so-called population mean or variance or not. So these are the questions that are initially put up. Initially put up means before doing all these values estimation or finding the table, etc. The first step is you put a hypothesis over the question. Hypothesis is that yes, population mean, the sample is a representative of the population, and population mean and variance or the interval of the population mean and variance can be found out by sample statistics. जैसे आप ट्रस्ट करते हैं ना किसी डेटा सेट पे, वो ट्रस्ट का इश्यू आता है। तो जब तक आपको जैसे हम लोग के लिए वी यूजुअली कॉल इन आवर जुडिशियल सिस्टम एट nobody is guilty until proven, isn't it? So with the similar concept here, until unless you do not give sufficient statistical evidence that your sample is not representative of the population, okay, until then you have to believe in your samples data set. This is what is expected. So in often in the cases of statistics, we usually work with these statements that I mean, we are not concerned about the actual bound of the constructed interval, but rather with whether interval contained the expected ratio of the variances or population mean. So in your probably in your case of a least square adjustment, as I've told you, we are more interested in finding out this. Okay. We want this case in this statistics, we want this range of interval or the ratio of the interval to be within a particular limit, statistical limit. If it is not uh, equal to 1, if it is not equal to 1, then this limit has to be explained. Okay, so that is the actual values of the interval are not as important as is answering this question is the sample statistic consistent with what is expected from the population. Okay, that means we are more focused toward uh, finding out this or answering this question is the sample statistic is consistent with what is expected from the population. So this procedure to use this validity of the statistics is known as hypothesis testing. As I've told you earlier also, while starting this module of hypothesis testing, is that we are more interested in finding out this answer, that whether my adjustment procedure is okay or not, rather than what is the value of the sigma naught hat square. So we are not more interested in this value. Instead, we are interested in whether this is within that range or not. So it has five component in general, five stages. One is null hypothesis. Then alternate hypothesis. Then test statistic. Fourth is rejection criterion. And fifth is test decision. So null hypothesis is H naught, which is a statement that compares a population statistics with sample statistic. This implies that sample statistic is what is expected from the population. We generally believe in the sample statistic. We do not deviate from this. Okay. In general, we say that this ratio would be 1. Alternate क्या होगा? Now, when we do not have any uh, supporting evidence, we can claim our null hypothesis. We have to give the client the alternative hypothesis. That means HA, alternate. HA means alternate hypothesis is what is expected when a decision is made to reject the null hypothesis. When you made a decision to reject the null hypothesis, then what will you give to the user? Okay, so thus represent HA thus represent as an alternate population of data from which the sample statistics was derived. The test statistics, third one is whether which statistic based on the problem will be using T statistic, chi-square statistics, or any other statistics that are in the picture. So the statistic in you that will be used is computed from the sample data and is the value used to determine whether the null hypothesis would be rejected. That means if we talk about the chi-square or if we talk about the T, आपका अगर रिजल्ट इधर पड़ा इस जगह आपके अगर आए तो रिजेक्ट है आर में लिख के आर लिख के दे रहा हूं और अगर बीच में आया तो एक्सेप्ट हाँ भैया बोलो So if your values help you suggest that the values are in this range, in this region, then only you will accept it. So these range are range area where you will accept your hypothesis. You want your if you want your if you want your null hypothesis to be accepted, that means you need your statistics to support your answer in between this region. Okay. Rejection criterion is obviously what is the rejection criterion? As I've told you in the case of what is the what is the statement that we have written? chi square should be greater than chi square alpha is equal to alpha. This is the rejection criterion, isn't it? In the previous case, here, this is your rejection criterion. Sorry, this is your rejection criterion. You do not want anything in between here. So this is chi square value greater than chi square alpha. This bar is chi square alpha. Okay. And then test decision rejection criterion is uh, that comprises the practical result of the test. This is statement about uh, whether the observation agrees statistically with normal distribution theory or not. If the test fails to reject the null hypothesis, there is no statistical reason to question the normality of the data. Okay. So these are the 5 steps. These are the 5 steps. I'm just taking 5-minute break, so that we'll continue from here. I'll take little extra time today. So we'll finish quickly. There is no issue. Okay, so as I've told you, these are the 5 steps for hypothesis testing. One is null hypothesis, alternative hypothesis, test statistics, rejection criterion, and test decision. Okay. So in this case, there is a whenever a test decision is made concerning the null hypothesis, there is a possibility of making a wrong decision also sometimes, isn't it? Because when we try to uh, decide whether we are going ahead with our null hypothesis, sometimes we go with the false positive also. We this is our tendency, isn't it? Just like in this your COVID pandemic, what happens is sometimes there are very positive cases, sometimes there are false positive cases are also reported nationally. If you see the statistics, very quite devastating that the false positive cases are very large, it's not very small only. Okay, so there is a possibility of making a wrong decision, since there can never be 100% guarantee. What should I say about the statistics or a test? So generally, what happens is we know that when we are saying about decision making, or possibly the chi-square, let's say this is chi-square. So when we what is expected from us, it is expected it is it is expected that we make decision from here. But sometimes what happens, because of some false positive cases, we get results decision that is made from here. So that is the case which we have to avoid. Uh, so there is a 5% chance that, let's say if you are working with 95% case, so there is a 5% chance that the decision was wrong. I mean, obviously, that is always a case that when you work with a 95% probability, sometimes what happens that you decide according to 95%, but chances is 5% that you made a wrong decision out of 100. So that is, it is possible that larger than expected ratio of the variances is consistent with population. This region which we try to devise, that when to decide whether our population variance, ratio of population variance and sample variance is consistent with the population, uh, statistical testing is needed further to avoid these kind of errors. So two basic errors are there. One is called as type 1 error, and another is called as type 2 error. Okay, so there are two types of errors there. One is called as type 1 error and type 2. So if type 1 error is when H naught is type 1 error is H when if the null hypothesis H naught is rejected, if H naught is rejected, but in fact it is true. So what you will mean by this, when H naught is rejected and in fact it is true, it is the type 1 error is committed. Okay, and if the null hypothesis is not rejected when in fact it is false, we call it as a type 2 error. So this type 1 error is again type 1 rejecting the null hypothesis when it is in fact true, symbolized by alpha. Type 2 error, not rejecting the null hypothesis when it is in fact false, symbolized by beta. कैसे? आइए फिगर से समझते हैं. ये टी डिस्ट्रीब्यूशन है. आपने डिसीजन यहां से दे दिया, इस वाले रीजन से, तो आपने टाइप 1 एरर कमिट किया. आपने नल हाइपोथेसिस को रिजेक्ट नहीं किया है, बट इनफैक्ट वो दूसरे किसी अल्टरनेटिव पॉपुलेशन को बिलोंग करती है. आपने इस वाले रीजन को मानते हुए आंसर दे दिया है, वो बीटा. क्वेश्चन समझिएगा. फर्स्ट केस पहली बात करते हैं. लेट मी जस्ट back a little bit. Let's say ये केस था. Just a moment. So when we are accepting the result, our job is to accept the result from this portion. Okay. Again, the same theory. If this is a t distribution, you have to work with a t table, and with 95% probability, you do not have to make decision on the 5% probability level, or for the time being 2.5% and 2.5% if it is a t distribution. Okay. We do not have to make decision from here. But if we made a decision from here, that means rejecting null hypothesis, but in fact it is true, then it is a type 1 error. Alternatively, if your sample doesn't belong to this population, in fact your population is different, this population, your sample is from this population, instead of rejecting it, you are accepting it with this region which falls in this proportion. This is called as type 2 error. This is the difference between two type errors, type 1, type 2. Okay. So these are to be avoided. You do not commit that kind of error. So the power of test is also known as 1 minus beta. Power of the test means instead of instead of accepting the wrong population distribution, you are rejecting it. So although these hypothesis testing cannot be explained in a simple one go, you have to devote little time, then you could get little understanding. Let us take one good example that would help us in finding out the uh, your understanding. So suppose a baseline of a calibrated length is is given as a baseline of calibrated length 400.008 meter is observed 20 times. What happens if this baseline is observed 20 times? Okay, with EDM instrument, the average of 20 observed distances that are properly reduced is with standard deviation of. So one calibrated distance is of this length is measured 20 times by an EDM instrument, and it is mean of it is found as this one with standard deviation of this one. A question is the reduced distance different from the calibrated distance at 0 point alpha level of significance? इसको अटेम्प्ट करिए आप लोग। तो नल हाइपोथेसिस कैसे बनाएंगे? एच नॉट आप कहेंगे कि वी ट्रस्ट अवर डेटा सेट, दैट मींस म्यू इज इक्वल टू 400.012। अल्टरनेट हाइपोथेसिस क्या कहेंगे? नहीं है इक्वल जो आपने मेजर किया। मीन की बात है, टी स्टेटिस्टिक क्या कहती है? y माइनस वाई बार माइनस म्यू अपॉन एस बाई रूट एन। कैलकुलेट करिए। y बार है आपका, म्यू है आपका, s क्या है, रूट एन क्या है। कैलकुलेट करने के बाद ये वैल्यू आई 8.944। ठीक है। नाउ विद अल्फा परसेंट सिग्निफिकेंस, विद अल्फा परसेंट सिग्निफिकेंस आपको डिसाइड करना, थोड़ा बताइए जरा कैसे होगा। When we see the table, that means, आप देखिए टेबल क्या है. So 19 degree of freedom, because 20 were the observation. So n minus 1 is mu. So 20 minus 1 19. अल्फा बाई 2 क्या होगा? 95% है तो 0.025. 0.025. अल्फा वुड बी 0.05 और अल्फा बाई 2 वुड बी 0.025. ये वैल्यू आ रही है 2.093. दैट मीन्स your value of 898,944 is greater than this t alpha by 2 comma mu value, यानी कि t is greater than t alpha by 2. T is greater than t alpha by 2. Okay. Rejection criterion: the observed distance is statistically different from the calibrated distance. The field and office position should be checked, and uh, you have performed this test. And if in checking no discrepancy are found, instruments should send to the manufacturer for repairing. This value should be less than 2 point critical value of 2.093. So this is just one example. Many more examples are available in the book. I'll send the details to Sumit for you can attempt many more problems. In fact, on Tuesday, 2-3 problems would be explained again. But before that, it is expected that you revise from the book. There are 2 books are uploaded. You should revise from that book, and then maybe you can think again with a different perspective. Okay. Any questions?